Hello, my name is Francisco Romero, and I will be presenting Optimizing Video Analytics with Declarative Model Relationships. This is joint work with Johan Oswald, Aditi Partap, Daniel Kang, Matej Zaharia, and Christos Kozirakis. Over the last couple of years, there's been a large demand for exploratory video analytics, namely, how do we extract value from video data? The way this has been done is with an application approach. For example, a traffic analyst might ask the question, how many cars turn left at night on Monday? If they want to coordinate stoplights. A sports analyst may want to search for Ronaldo's headers when he played for Juventus. A TV news analyst may want to analyze demographics and news, asking, find clips of Jake Tapper interviewing an angry Bernie Sanders. Let's focus on the query shown here and see what it's like today to optimize complex, multiple predicate queries. The SQL code on the right that you see here is what you would write today. It requires three models: an object detector to count people, a face detector to identify Bernie Sanders and Jake Tapper, and an emotion detector to identify the angry emotion. The original query that we are going to run is shown on the right. You first run object detection, then you run face recognition, and finally emotion detection. We see the performance is about 270 seconds. We would like to meet an 80% accuracy target, denoted by the dotted line, where the 80% accuracy is measured with respect to this original plan. The first thing we can do is the standard predicate reordering. We see here that reordering the face recognition and object recognition gives us the best predicate reordering, improving performance by about 5.4x compared to the original plan, and it meets our 80% accuracy goal. So this is a great plan, but can we do better? Another optimization is model replacement, where a cheaper but less accurate model can potentially replace a slower but more accurate one. For example, here, we can replace the original emotion detector with a cheaper version. Unfortunately, not only does this replacement not improve performance, it doesn't even meet our accuracy constraint. So this is a bad replacement. On the other hand, if we try to replace the object detector with a cheaper version, we see it both improves performance by 1.1x over the best predicate reordering, and it meets our accuracy constraint. So this is a good optimization. The third thing we can do is consider using filters, which are cheap models that can get rid of frames that do not contain the predicate we are considering. Let's consider filters for the face recognition model, starting with a HAR filter that filters frames with no faces. Unfortunately, while it meets the accuracy goal, performance decreases. And in this data set, most of the frames contain faces, so it filters practically no frames. Thus, this plan should not be considered. Instead, if we use a similarity filter that filters using a cheap pixel-wise detector, we'd see it meets our accuracy goal and improves performance by 1.5x compared to just replacing the object detector. So overall, this plan improves performance by 9x compared to the original unoptimized plan. The importance of optimizing video analytics queries has been observed in the data community over the last several years, with many proposed point solutions, say for object tracking, indexing, and sampling. For these solutions, the goal is, how do we optimize a single model while still meeting our accuracy goal? While point solutions are great, the problem is twofold. First, the benefits of each optimization are query and dataset specific. For example, the HAR filter was not good in this dataset because there was a lot of faces, but it could be in one where the faces are scarcer. Second, because you have to do this for each query and data set, it is very time consuming and requires a lot of expertise to get right. We walked through 6 different plans in the previous slide, but in reality you'd actually have to consider close to 100. And the reason for this is that there is no way to express domain knowledge to a system, and a systematic way to be able to explore this domain knowledge is missing. To address this, we propose optimizing queries with declarative relationships. To express domain knowledge, we propose relational hints, which are a declarative interface for expressing ML model relationships. To use this domain knowledge, we propose Biba, a system that uses hints to optimize video analytics queries. The end-to-end workflow for how Biba uses relational hints to optimize queries is shown here, and we'll start with discussing relational hints. There are two kinds of relational hints. The first one is model replacement, or a can replace. This can be used if two models have the same output format, for example, both produce labeled bounding boxes, and at least one common class. Let's take a look at an example. If I would like to detect a basket being scored, one way to do this is to use an action recognition model, where I pass it a batch of frames, and then I look for the ones that are labeled basket scored. However, this might be an expensive model to run. So an alternative way to detect a basket scored is to use optical character recognition over the score bug. If the score changes, for example, from 86 to 87, we can label a basket as being scored. Expressing this to a system is as simple as this one-liner, where we say score change OCR can replace score action recognition. Note that a system cannot figure this out automatically, as it is domain knowledge. The second type of hint is input filtering, or a can filter. This can be used if models have a different output format, for example, one produces labeled bounding boxes and one doesn't, or if they have the same output format and disjoint classes. Let's say we would like to find Bernie Sanders. A standard way to do this is to use a face recognition model that produces labeled bounding boxes. This can be unnecessarily expensive though, especially if a lot of frames have faces other than Bernie Sanders. A cheaper way to do this can be to use the transcript. We can search for mentions of Senator Sanders and only process those frames with the face recognition model. This is again expressible with a one-liner, where transcript search can filter for face recognition. And once again, this is domain knowledge that is not going to be figured out by a system. These two hints offer a simple but powerful interface that capture many optimizations. For example, can replace captures model variants, proxy models, and indexes. Can filters capture binary filters and using area expertise like transcript search. This enables significant optimization opportunities. Now let's discuss how Biba uses the two hints to automatically optimize video analytics queries. The first step is plan generation. The challenge here is how do we incorporate hints in query planning? To explain this, let's use a simple example as shown here, where my query has two models, A and B, each with their corresponding predicates. Biba first generates a model tree as shown here, where A feeds into B. After this, we will permute the predicates and exhaustively apply the hints, which is order agnostic since we may end up applying multiple hints per plan. In our simple example, we have a can replace and a can filter hint. The first generated plan simply permutes the predicates. The second plan then applies the can replace hint to the permuted plan, which replaces A with C. The third plan then applies the can filter hint, adding filter D before model B runs. Now that we have all these different query plans, the challenge for the optimizer is selecting the best plan that meets the user's requirements. The first step is to estimate accuracy. Biba does this using a canary input, which is a short clip that is representative of the user's query. Biba uses the canary when comparing the original unoptimized plan to any newly generated plans. After this, Biba will estimate selectivity and compute the cost per plan. The cost is given by the following formula. The sum of the product of the latency of each model, which is acquired in a one-time profiling step, and the number of frames needed to be processed. The number of frames to be processed is based on the selectivity of the model that ran before it. The first model will process all frames. Once computed for all the plans, we can select the best plan based on what the user wishes to optimize for. For example, cost, latency, and performance per dollar, while ensuring the accuracy goal is met. To ensure this is done efficiently, Biba applies pruning techniques based on the estimated accuracy and cost. This allows it to process hundreds of different query plans over an hour of video in less than 2 minutes by the optimizer. For more details, please see the paper. Biba is implemented on Spark and deployed on Google Cloud. We consider 4 different applications, each with their corresponding queries. The number of hints per query is also shown, as well as the corresponding number of plans that Biba has to consider. The number of plans depends on the number of hints, the number of predicates, and whether the predicates depend on each other. For example, first we must run object detection in the traffic query before running object tracking. Also shown are sample hints for each query. For example, with the traffic query, we can first run a motion detector to detect cars and people before proceeding to identify them in a frame using an object detector. Let's compare Biba to state-of-the-art systems. We will compare Biba to 3 different baselines. Upper PR, which is the worst case predicate ordering of the original query with no hints. Best PR, which is the best case predicate ordering of the original query, also with no hints. And EVA, a recently proposed video analytics system that does feature predicate reordering with user-specified models per accuracy goal. So for higher accuracy goals, it will use higher accuracy models. All of these baselines met the accuracy goal of 90%. And what you see here is that Biba achieves up to a 4.8x speedup by using relational hints across the 4 queries. This performance improvement is inclusive of planner and optimization overheads. For traffic, Biba uses a faster brightness detector and object detector from a can replace hint. News and sports use a proxy index from Tasty, a previously proposed point solution. The bias query uses a model layer sharing approach, where the last few layers are specialized per predicate and the common layers only need to run once per query. This is expressed using a can replace. Now we can look at how Biba trades off latency and accuracy. The x-axis shows an increasingly stringent accuracy target, and the y-axis shows the query latency, where lower is better. In the news analysis case, we see the performance degrades as the accuracy requirement increases. However, Biba applies the right hints to improve performance over EVA. In the traffic analysis case, Biba determines the same cheap model can be used while still meeting the more stringent accuracy requirements, while EVA uses the expensive, more accurate models, which results in a 4.8x improvement in latency. So Biba selects the best combination of hints as the accuracy goals vary. In conclusion, we presented relational hints, which allow users to declaratively express domain knowledge about model relationships. Then, we presented Biba, which automatically determines how and when to use relational hints to meet user goals. Biba improves performance and cost without sacrificing accuracy. Check out some of our recent online coverage of Biba, a blog post, and how we use Biba to process hundreds of hours of video in a minute. Thank you for listening.